Start streaming. Okay, let's try this again. What I should expect is to see this live stream appear on my YouTube channel. Do I see that? Yes, I do. I think I'm starting to see it. In order to confirm whether I'm actually seeing it, I need to check my actual YouTube channel. Is it there? Yes, it's there. It's on my live channel. Great. So hello, welcome. I'm Ezra, or Hevadir as you subscribe to. I'm going to, basically we're going to be doing something a little bit experimental. I've been making a lot of these complicated stuff on websites using these big graphics in Desmos, and that's really fun. But here's the thing: you're not supposed to make such large scale graphs using a 2D canvas. Does that make sense? So let me put it like this: we're here today because we're going to be learning how to code in WebGPU. What is WebGPU? It's relatively recent to Chrome. Google just added this feature to Chrome, which allows you to use your graphics processor to actually create graphics, that's the key to speed. You can get really, really fast visualizations with that. And it's been a long time coming since I've actually learned how to accomplish that myself. And I really want to accomplish that. It's on my bucket list. So what I have to say, Google just released a guide on how to make Conway's Game of Life. Rest in peace. And it just is an introductory to WebGPU, but not only that, an introductory to graphics as a whole. So I want to try it. And what a better way to get the gears going than to live stream myself, walking through a bustling area. I'm going to post a link to the guide that I'm following in the chat. Let me look for it. Let's see, close. Yeah, let me just repost the link in case you missed it at first. Where is it? Chat. Awesome. Grand. All right. How hot's my phone? Pretty hot. And I'm going to turn the quality down because I don't want to get double. All right. Without further ado, let's begin. So this is where I'm standing currently. I have a grid of squares, 16 by 16. I can specify that in my code using whatever value that I want. But this is good for now. And what else do I want? So now we're actually going to color these and make it a little more exciting, because right now it just looks like it's red. One of the things that we're going to do is we're going to make it colorful. How do we do that? We use a fragment shader. So let's follow the guide. This is a new part of the guide, starting it fresh. Part 6, make it more colorful. If you want to follow along, look at the guide in the comments. At this point, you can easily skip to the next section since you've laid the groundwork for the rest of the code lab. But while the grid of squares all sharing the same color is serviceable, it's not exactly exciting, isn't it? Fortunately, you can make things a lot brighter with a little more math and shader code. This is the big thing. We are able to, what this is basically saying is we're going to be able to color every single pixel very fast, because right now I only have it programmed to a single color. But GPUs can do a lot more. You'll see. I'll see. I'm going to learn this as we go. Use structs in shaders. Until now, let me make this bigger for you actually. Until now, you've passed one piece of data out of the vertex shader by returning it. A vertex shader is always required to return a position, so if you want to return any other data along with it, you need to place it in a struct. Structs in WebGSL are named object types that contain one or more named properties. The properties can be marked with attributes like built-in or location. That @ symbol has been used a lot previously. And I think they're just keywords or declarations that you can use inside of it. I'm not exactly sure, how can I explain this? Let me go inside the code here. We see this is again all from the Google guide. We see this @ location and @ binding, and they take in an argument, right? They're a function because after the binding or group, there's a parentheses and 0. The guide just tells you to set to 0, but those numbers are important because they're actually what we need to access. We access them at those numbers, if that makes sense. So what's the guide telling us? That there's properties we'll be able to use like that syntax for the at group or at whatever. So let's find out. What we're going to do is see what that group binding is. So this line we already have, I think, in our shader code. Yep. It's continuing from the last part. Vertex. So this is going to define a vertex shader function. Takes in arguments of location, which is a vector 2, built-in instance index, which is which square it is, because we're actually looping through a bunch of squares. And then we convert that. Express the same thing using structs for the function input and output. So I guess let me just copy this and see what happens. Where is it? So I need to see if the code looks the same. Are these identical? Cell, grid position. What's different about it? Instant index. I think it's the same. So I'm just going to not paste it and see how that goes. What next? Index, vertex. So we have a vertex input. This also goes inside of our shader. Okay. Whoops. Let me copy this portion, and we're going to see what this does to create colors in our squares. It's going to do something. Hold on. What do I need? Go back to the code. Whoa. Here's the code. So let me put this, put it at the top. Let me put it after the vertex shader, because we're going to be editing our fragment shader. That's the function on the very bottom. That's what we need to edit. Vertex main. Whoops. Oh no. Oh, this is also a vertex shader. Wait, did I just paste in 2 vertex shaders? So I think we just overwrote the initial part. Vertex input is a structure. It takes in a location at position 0 called position, and a built-in the instance index at, which is an unsigned 32 integer. Group binding is a uniform. Uniforms are something that we can supply into it. That's kind of like, it's kind of like a static value. You grab it from JavaScript, which is the coding language you use this on, and it grabs it and yanks it into the GPU component. What next? Vertex main. It takes in an input. Oh, here we go. Okay, it's going to be a lot more clean now. It takes in a vertex input, which is, what does that look like? It takes in a vertex input. So this over here, let me zoom in a bit so you can see it better. And let me hide the console. You don't need to see that. It's the updater. It takes in an input, structure that we've already defined. It contains a position and a built-in position argument, which is a 4 vector. I don't know exactly, actually. We'll see what that does. But it takes in the structure that we've just created, and it outputs a vertex output. That the right arrow is yield. It's what it goes into as. So, fragment main. All right, so it starts off doing the grid. This is just like grid math, like floor and mod. It lets you create a square of grids. That's what the modulo is, and that's what the floor is for. But now the var output. It sets var output. It casts the type of var output as vertex output. However, only in the next line do we actually assign a value to it. First, we're just typecasting it. We typecast it as vertex output, and then we set the position of that to grid position, which is a 2D vector, plus these final 2 components, which makes it, what's that? That makes it a 4-dimensional vector. Great. Let's see. Great. We're still good. Still doing this basically. Index.html. All right, so we copied that, great. Pass data between the vertex and fragment functions. As a reminder, your fragment function is as simple as possible. Vertex. This is, okay, great. So let me get rid of the original vertex main, right? Oh, this is just, damn it. Okay, yeah, let me comment out what I already had. I need to do that. I forgot about that. So what we just pasted is essentially already used inside of it, so we don't need to use it anymore. Sorry, the function that we pasted from the Google Lab is already what we had in the file, but without the comments that they provided before, the ones that I wrote inside of it, so it's hard to like tell immediately. Fragment main. What do I need? I need to get location. So going back to the guide, we have a pass data between a vertex and fragment function. This is the fragment function that we originally had. You are not taking any inputs, you are passing out a solid color red as your output. That's what this is. This is RGB with an alpha of 1. If the shader knew more about the geometry that it's coloring, though, you could use that extra data to make things a bit more interesting. For instance, what if you want to change the color of each square based on its cell coordinate? The vertex stage knows which cell is being rendered. You just need to paste it along to the fragment stage. So to pass any data between the vertex fragment, you need to include it in an output struct with the location of our choice. Since you want to pass the cell coordinate, add it to the vertex output struct from earlier, and then set it in the vertex function before you return. Change the return value to vertex structure like this. Change the return. New line. Output. Okay. I see something new here. It's telling me that there's a new line here, output.cell. Output.cell is a new line which comes right before we return the output. Since this is a struct, good. Okay, we can modify the properties of a struct. Output.cell is now equal to cell, which is the position of, wait. Oh, hold on. Aren't I already returning that? Oh, okay. I see. Output.pose. There are two like properties of output. There's position, which is actually its canvas position, but then there's cell, which is its local 2D space position, which is different than the output cell. So they're not the same. And I assume that output cell is important because we're probably going to be operating on that guy. So let's do so. Returning back to the guide. 1 second. Ooh. In the fragment function, so this is our fragment shader function, receive the value by adding an argument with the same location. The names don't have to match, but it's easier to keep track of things if they do. Let's see. Fragment main. Fragment main takes in a cell, which is a vector 2, and outputs a location, which is a vector 4. Since fragment returns values red, green, and blue alpha, since cell is a 2D vector, this is equivalent to red cell, Y cell. Oh. Okay. So I go to my fragment shader. Sorry I'm squinting like this. I got like angry face, but it's because I'm sweating like a pig. Return that. Cell 4 vector. Cell vector 4. So if I return that, refresh the page. Oh, wait, what happened? Uh-oh, I got an error. Crap. I need to show my console for the error. They log anything you do wrong. Return out, expected a semicolon for assignment. Did I forget a semicolon somewhere? crap. Where did I forget forgot a semicolon. It's no JavaScript. You actually have to watch out where your semicolons are. Now what? Oh, tint WGSL failure, 43 error. Let me make this larger for you. Shader cell is invalid. While validating the vertex stage, while calling create pipeline is invalid. Cell pipeline is invalid. Oh crap! I wish I could diagnose these. Okay, hold on. These are made easy. These errors are intended to be straightforward. All right, how do I do this? What did I do wrong here? Cell vector 4. What did I get wrong? I can't see what I got wrong. Did I define it twice? No. They're all that's commented out, so that shouldn't be an issue. Cell shader is invalid. Vertex state, create pipeline, cell pipeline. Cell pipeline's invalid. Validating get bind group layout is invalid. While validating cell render bind against group. Hold on. How do I do this? Crap. What did I get wrong? All right, let me follow the steps again. Shouldn't that work? Cell. This returns cell. What do I supply to it? What do I supply to the fragment shader? I supply a cell. So this should comment out correctly. Let me return this again. Hold on. Hold just your horses. This is grid WGSL. Fragments. Refresh the page. Refresh. No, same error. Struct number cell not found. It appears to be indexing. Was that the error I got last time? That's the error I got last time. Okay, output.cell. Cell is not found. Cell isn't one of the elements of that. Of its input. Cell is a vector 2. So where do I call in fragment main? In my code, right? Fragment main is called right here. Vertex main. Instead of vertex main, what did I call it? What the hell? Shouldn't that work? I have no idea why that doesn't work. Fragment. To let I equals to a float 32. I actually have no idea why that's not working. Vector 2. Cell is a vector 2. Cell is vector 2. What the hell? What is cell? Wait, did I not do this right? Where is dot cell? Dot cell. Did I copy and paste the guide wrong? Where's dot cell? Output dot cell. It's output dot cell is equal to cell. Where did I define cell? Cell is a vector 2. Crap. Okay. What the heck did I do wrong? Let me slow down here. Let me set this to a constant again. I gotta slow down. I need this to be a constant value. The output of the fragment shader, just return to one color. Does one color work? No, it doesn't. So that's not the issue. The actual issue is the output.cell. I'm not allowed to do output.cell because the property doesn't exist on output. So where is it? So I'm going to keep that there then. Cell should be a vector too, which fills in the other two values, but where is the output for Shice? Okay. I don't know. So I can't assign output.cell. So let me just comment this out. What happens? Also an error. Let me retry the error. Hold on. Crap. Fragment input location doesn't have a corresponding vertex output. At location doesn't. What the hell? Damn it. Okay, how do I do this? How do I do this? I think I have to sit down for this. Like, I'm not exactly sure how to do this. Crap. Okay. I need to think here. How do I do this? Shit. Vertex.pose doesn't exist. Let output pose. Can I just hold on? Let me undo what I did. Let me find some shade as well. What I need to do is what do I want? Grid. Vertex. I gotta stay still for a second. Hold up. Too much movement. Vertex output is equal to that. Alright, let me just try. Why am I returning a vertex output? No, I want to return a vector 2. A vector 2. Is that the syntax for it? Built-in position vec2. How do I return it actually? Vertex. What did I have before? Let me revert to what I had before. Just let me get this. Let me delete that part and just have this. Does this run? This doesn't run. So alright, let me rewind back in time. I did something to screw everything up. That's my previous work. Good. Just this. Fresh start. This works. I now need to slow down. I'm going to create two structs that go at the top of the file. Two structs go right here. Vertex input, vertex output. I should run. Those structs are being called. Beautiful, it runs. However, comma, when I assign this to return a vertex output, like so, so instead of returning a built-in position, I'm still, oh, this functions as if there was an @ symbol. So I return that. Now it should not work because, hey, I'm not returning a vertex output. Let me return a vertex output. That's what I need to do right now. I make vertex output, return. Instead of returning just the grid position, I do this, which assigns the position to the output. There shouldn't be an error now. There's not an error. Good. Now, comma, I need to actually get the grid position. Cell. This is like the local position. Doesn't work. Cell, struct members not found. Instance. Oh, so not yet. Oh, did he that's why. He changed the vertex output. That's why. Cell didn't exist because cell wasn't there. There we go. That would have saved a lot of headache. He missed. I read over that code and I thought it was redundant. I thought I didn't have to need that. All right. So instead of that, let me. Okay, I think I could start going again now. I got that hiccup out of the way. How many frames have I lost? Oops, don't want that. Ooh, pretty good. Dropped only 10% of the entire live stream. That's pretty good. Let me see what else. Yeah, this is I got a streamer set up, all right? I don't even know if I'm pushing the right amount. Okay, so now, beautiful. Now I can return the vector 4, but instead have the first two arguments be the cell position. Let me refresh it, and it should work. Crap. Unresolved identifier cell. Crap. What did I want to do? Cell didn't work. Okay. Remember, fragment returns blah blah blah, cell x, cell y. Alternatively, you can use a struct method instead. A frag input. I'd rather do that. You know, this is more explicit. A fragment input is a structure which takes in. Yeah, I'd rather do this, right? Like this way you actually like define like the struct of it instead of just doing like a generic out at location, at fragment, whatever. You just do the rest of it. Shit. So if that doesn't work, what do I need then? Input cell becomes 0 and 1. Crap. Cell 0. Cell 0 is equal to 0 and 1. Did I forget something else? I definitely did. It's input.cell, frag input. This still isn't going to compile though. I'm going to get the exact same error. But at least, I don't know. These are more readable to me. Like, kind of. Refresh. Same error. Refresh the console. Unexpected token. Oh, thank you. I added an X inadvertently. Good error. Oh, whoa. That actually worked. Hold on. What happened? Oh, wait. I think it's black. Oh, the squares are black now. Crap. That's also not my intention. The squares are black. That means it's rendering at least, but it's not actually doing the input correctly. Damn it. Vector 4 is equal to input.cell 01. Input dot cell 0, 1. Cell is a vector 2. What do I supply it? I supply it with a frag input. But frag input's empty. Where do I supply this? What does the guide say? Another alternative, since in your code both these functions are defined in the same shader module, is to reuse the vertex stages output struct. This makes passing values easy because the names locations are naturally consistent. Fricking hell. Input cell 0, 1. Fragment main is equal to input output. Fragment takes a vertex output. Wait. So, no, it should take a vertex output, right? Take a vertex output instead. I want to get a vertex output. Then what do I get? Crap. Refresh. It's the same bloody thing. It's black. That's not what I want. Where's the result? It should look like that. It doesn't look like that. Okay. What's going on here? What's going on? What's going on? Oh, hi, Raiden. Oh, sorry if I missed your comment. I'm coding the next... Yeah. This... My legacy. Yes, I'm coding the next top 10 Minimator. Jeez. Yeah, wait, Raiden, what's your name on the forums? Are you on the forums? I might remember you. Unless you're recent. I don't recognize that handle, but if you tell me what your Minimator forums is, I may recognize you. There are more colors now, but that's not exactly nice looking. You might wonder why only left and bottom rows are different. The color values you return for fragment. Expect the channel. So I didn't get that. I literally didn't get that result, so I did it wrong. So I just copy this whole thing, because obviously I'm missing something. Copy the whole thing. Dot cell. Blah, 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 blah. Save, refresh, error. What did I do wrong? Wait, hold on. Something happened. Something happened to... What the hell happened? I did something wrong before. What? This is my old code? Do I just have to uncomment this? Does this work now? Or no? Now it's going to give me an error. Oh, so I just forgot to... Frag input is just a... Could do either way. All that works. So it's colored now. So I've actually colored the squares. I didn't think I'd actually manage to do that. Okay, so what do I want then? Okay. What I need to do is get my fragment function. So I just copied it and it worked. So what's this doing? This is taking the RGB, red and green. The red should be this part should be black, and this is the RG. And when you mix red and, let me get my color picker, this should actually be, yep. 255, 255. Okay. So that actually worked in the end. That's a relief. What do I need now? What I need to do is continue. There are definitely more colors now, but it's not exactly looking nice. You might wonder why only the left and bottom rows are different. That's because the color values that you return from the fragment function expect each channel to be in the range of 0 to 1, and any values outside that range are clamped to it. Your cell values, on the other hand, range from 0 to 32 along each axis. So what you see here is that the first row and column immediately hit that full 1 value on either the red or green color channel. And okay, makes sense. Basically, why are we getting these colors for it? Because it's literally like clamping where the 0 and the Y is on, or whatever. Okay, nice. But that is not what we want. What we want is something else. We want to make it actually look nice. Maybe give it a slow gradient instead. Let me try that actually. Is this a shady spot? I think this is a shady spot. Yes, it is. Okay, kind of. Yeah, it is. All right. So if I want to get a shady spot, what do I need? Let me do like a gradient. So instead of this excessive amount, let me just divide the parameters by something. Let me specifically, it goes from 0 to 1, right? So the cell's maximum is the grid size, and we have a grid size. We defined it as our uniform grid, and we can divide that, since these are both vector components, it's going to divide their components. There we go. Very nice. So this is not actually, so let me make the grid smaller to actually see that we're not doing a per pixel shade. Not at all. We're not doing a per pixel shade. We're doing a per instance shade. Yep, okay. See how these, let me even make it smaller. Here we go. Okay. See how these squares, these squares aren't gradients in themselves. Each square is assigned to a single color, but that's it. It's not doing it. It's not like applying the gradient per pixel. It's only taking the actual position of that square, and then when you line them up all together, you're going to get that overall effect. That's what happens. So at 160 squares, let me here, I'm curious. Right now there's like a little margin after like each square. So wait, let me replace every 0.8 with 1. There's a fast way to do this. Replace it with 1. Bam, 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 bam. Nice. Save, refresh. There we go. So every square is a pixel. I don't know if this is the way to do it. Like I've actually made a square. Those are actual squares. And you apply like a vertex. I actually do like a vertex fill for each of those squares. Probably not what you want to do. Probably. Although if I set this to really low, we should get like a pixely yeah, there we go. Whoa. Look how pixely that is. Oh, beauty. Damn, look at that. So if I do a grid size of 4. So I doubt that's the real way to do it. Like, there is no margin. Like, I think you need a margin. Or, sorry. You don't want to draw every pixel as if it were connected by 4 vertices. That seems like excessive. So undoing that, and now we have the margin again. Well, let me make it smaller. Now we have the margin again, like that. Nice. Okay, cool. In that case, there's something else that I should do. Let's see. There are more colors. If you want a smoother, divide by the grid. Aha, it read my mind. There we go. So I got that already. It could be either CSX. Try both. Pick the one you prefer. Add brighter colors to the fragment shader like this. 1 minus. Right? Let's go back to the shader. C is let is for constant. Let C is equal to input.cell divided by grid. Cool. And now we can do C. This becomes C, but then this becomes 1 minus CX because we're just grabbing the X component. Whoa, very nice. Whoa. That's a sexy grid. The result looks quite nice. This isn't a critical step, but because it looks better, it's including the corresponding checkpoint source file, and the rest of the screenshots reflect this more colorful grid. Got it. Oh, it's so much better when it actually works. All right, let me just can I just pop this chat out? I don't actually want to close. Yeah. I don't actually want to watch the stream in my stream. I just want to see the chat. Good? Yeah. So what do I want now? What I want now is to take a drink and continue walking. Because that's the mission of this, to walk. To walk. Okay. Time to continue. Yep. All right. Nice break. Part 7. Manage cell state. Next, you need to control what cells on the grid render based on some state that's stored on the GPU. This is important for the final simulation. So this is something I have no idea how to do. Like graphics, fine. I know how to draw pixels. I know how a canvas works, roughly. But actual GPU number crunching, totally new to me, totally new. And I'm looking forward to it. So how does it work? Let's see. All you need is an on-off signal for each cell. So any options, for Conway's Game of Life. So any options that allow you to store a large array of nearly any value type works. You might think this is another use case for uniform buffers. While you could make that work, it's more difficult because uniform buffers are limited in size. You can't support dynamically sized arrays. You have to specify the array size in the shader and can't be written to compute shaders. The last item is the most problematic since you want to do the Game of Life simulation on the GPU in a compute shader. Fortunately, there's another buffer option to avoid all those limitations. I didn't just comprehend what I read, despite my inflection. You could tell when I can't understand something. Create a storage buffer. Storage buffers are general use buffers that can be read and written to in compute shaders and read in vertex shaders. They can be very large and they don't need a specific declared size in a shader, which makes them much more like general memory. That's what you use to store the cell state. Note, if storage buffers are so much more flexible, why bother with uniform buffers at all? It actually depends on your GPU hardware. There's a good chance that uniform buffers are given special treatment to your GPU, allow them to update and read faster than a storage buffer. So for smaller amounts of data, it has the potential to oh, sorry, the taxi stopped there. I thought it was waiting for me. All right. Let's see. Wait. So, obstacle, so allow you to store a large array of nearly any value type works. Makes lots of another use cases. Uniform buffers. Oh, well, you could make that work. It's more difficult because uniforms are limited in size, can't support dynamically sized arrays. Aha. It can't be written to by compute shaders. That last item is the most problematic, since I want my compute shader to write to those values. Storage buffer. Okay, so we're not going to be using a uniform buffer because uniform buffers, they do not allow you to alter the content. A compute shader cannot alter the content of a uniform buffer. So why would you use the uniform buffer? If we're computing the Conway game of life in JavaScript and not a compute shader, then sure, you use that. To create a storage buffer for your cell state, use what? By now it's probably starting to be a familiar looking snippet of buffer creation code. First, you create the array, which is an unsigned int 32. Why do I need to be 32 ints? Isn't it more efficient if I make it 16 ints? Like, it's just on and off. We'll see. Cool. So let me make a copy of where I stand, actually, because I don't want to lose out on my progress. Well, I do want to lose out, but also like I want to see like if I irreparably damage this, then I would like to restart. So I'm gonna call this cool colors. Why not? Wrong folder. I don't know. That was the incorrect folder. What I need instead of that is to get crap. What is it? No. In my app folder, let me select app. I'm going to call it color-grid.ts TypeScript. Cool. Paste the file in. This is our backup. We're now going to be modifying our game of life instead. So, what do we need? Color grid, game of life. Bruh. What do I need now? Go to our shader, Google Chrome. Create an array representing the active state of each cell. So I'm going to copy this code snippet. I need to, where do I put this? There's shade here. Perfect. I need shade. I'm just starting to realize like this is a really bad idea. Where's shade? Let me create my compute buffer. Create an array to represent the active state of each cell. So why is this unsigned in 32-bit? Can I do 4? Whatever. Create buffer. This is going to be a cell state storage. Cell state buffer usage storage, buffer copy DST. This allows you to copy in values, I think. Okay. What I need to do is activate every third cell with the following code. You can populate for Q write buffer. Every third cell of the grid is active cell state array I. For every third cell, mark every third cell of the grid as active. Oh, okay. Gotcha. I think I got it. So this is not going to be the compute part. This is going to be our index, our initialization part. We need this to start off as something, but what does it need to start off as? Something. It needs to start off as something. So I'll copy it in here. It's the cell state array. Aha. So yeah, this snippet just populates. It just populates all of this, and if it populates all of that, cool. So that should, we're not going to see the result of that yet. Read the storage buffer into the shader. Next, update your shader to look at the contents of the storage buffer before you render the grid. This looks very similar to how uniforms were added previously. Okay. Aha, this is our first binding, our vector 2, uniform from JavaScript. This is our second binding from uniform, well, from which is an array of unsigned 32 ints. Again, I don't know why we're using 32-bit. It's just on and off. Maybe it's something internal. I don't know. All right, so let me go to. I have to make another copy actually. 1 second. I have to make a backup of the working shader. Otherwise, I'm gonna get totally lost. Backups are very, very important for this. Okay. Backup. Grid. No, I'm not going to call this grid. I'm going to duplicate grid. But this one I'm just going to call colored grid.wgsl. Whatever. I'll fix the naming scheme later. Did I just... God damn it. I copied the wrong file. Ay. There we go. Alright, let me get rid of this now. Yeah, let me delete that part. This is the color grid. It just does all that bit without anything extra.
Anton.
Alright. Well, now, go to my game of life. Here's the part where I need to actually write to the grid. So, it's going to be new line, very beginning, create uniform storage under the vector storage. But this time, what we're grabbing is an array of unsigned 32-bit integers. Now, first, you add the binding group, which tucks right underneath the grid uniform. This is describing what we did. And after you do that, you tuck it. You want to keep it the same group as the grid, but the binding needs to be different. The var type is storage in order to reflect a different type of buffer, and rather than a single buffer, the type you gave for a cell state of the array is unsigned 32 values, in order to match the unsigned 32-bit array in JavaScript. Okay. Sure. I assume like everything from the binding is just like we're gonna grab all of those with like the binding variable that we created earlier. That's my assumption. All right. Took a wrong turn, kind of. Whatever, it'll be fine. So what now? Binding grid uniform. Why 32? Ah, thank you. Why 32-bit ints? Doesn't that seem wasteful if all you need are booleans? Well, yeah, it is. But also, GPU only cleanly exposes data of a few types it can work with them fast. You can't specify that you're exposing an array of bytes, for example. That's why work with an array of bytes, for example, because it wouldn't work well with certain assumptions GPUs make about data alignment. Now you could save space and use bit masking tricks such as storing the active state for 32 different cells in each value of that array. There's actually a long history of developers finding clever ways to pack the data they need into GPU-approved methods like that. But that would make the example code more complex. Yep. History of developers. Yep, okay, this is kind of like what I learned in university. Like, you could stack in more values than it actually, like, be able to fit originally. Like, you can, if you have, like, 32 bits, you can cram in 2 values into that single 32-bit spot-ish, right? Like, you could do that. It just get, like, a little bit messy. You could save space. Oh, but that's more computing. And truth is, for a use case relatively simple as this one, you don't need to worry about the memory impact too much. Yep, this is a simpler case. All right, so they address the elephant in the room. That's helpful. Okay. Next in the body of your vertex function, query the cell state. Hold up. Oh, you go. Oh, that's my chat. I haven't checked you in a while. Nothing. Whatever. This is gonna be for me later, because I need something. If you happen to be watching this, like I need something that like captures like what I was feeling at the time. So it's been a while since I live streamed last time. Last time I live streamed was me doing my homework. If you don't count the Desmos one, which is different. Yeah, so anyways, I need something to like, oh, this is what I was feeling like at the time. And yeah, right now I feel like it's been long overdue. Because now I'm starting to get into coding, and I don't know, I kind of want to be like a coder now. I didn't think I wanted to be like a coder or a programmer or whatever, and now it's kind of like my interests are kind of like pivoting a little bit. I still like Desmos, and I'm going to be using Desmos for a while. I'm going to keep using it, but it's probably going to be like it's not like, I don't know if using Desmos is the end destination. Like I'm cutting myself short. Like I could be coding instead. Like, because there's a lot more. When you're too comfy, when you're too comfy where you're at, like you should ask yourself, like, maybe you gotta pump it up. We gotta push the envelope just a little bit. And yeah. So 32, state value can be cast to 32 in order to satisfy. Vertex main, blah 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 blah. So what's going on here? We cast instance as a 32-bit float, and then we do the modulo new line, and then we set the cell state of the instance. Oh, are we going to overwrite the cell states? What the heck? What do we do with state? State is equal to cell states. Where did we define cell states? I don't remember where we actually defined cell state. That's like new, isn't it? That feels kind of new. Shice. Okay, if cell state is new, then what do I want to do? Where is cell state? Am I going crazy? Like, I'm reading that and I don't see where we define cell state. Let me just scroll up a little bit. Did I just find? Oh, I did. Jeez, sorry. Fuck. I apologize. I didn't see where I defined it. I defined cell state in my uniform. I literally forgot that I called it cell state. So, okay, fine. I called it cell state. So now I'm going to actually overwrite the element of instance for cell state. That's not where I want to go. Cool, I was just about to walk through a door somewhere. Alright. So, what now? What now? Binding group. Shit, I'm in the sun too damn much. It's bothering me. I shouldn't be in the sun this much because my Mac is hot as sin. I kind of want to find shade, like just a little bit. Crap. There's shade right past this light. All right. So, who's driving there? All right. Okay. Shade. Good. So, first, you add the binding group, which tucks right under the grid uniform. Cool. What is my new line? My new line is with the comment that says new line right here. All right. Crap. New line becomes fraction. Where did I do that? I did it with I. Do that after cell. So when I define state, let state equals that. A vertex, aha! A vertex, my vertex shader is overwriting the value of my uniform, my uniform buffer. It can do that? That's impressive. This is a cooler view. How's this view look, actually? Okay. So, oh wow. I love that view. Okay. So if that's the case, cell shader, blah, 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 blah. New, scale the position by the grid's active state. Cell state instance. Okay. So, sure. I'm doing something a little bit different now. Let the grid position is now equal to the state of it. Whoops. What did that do? Add a storage buffer to the bind group. You can see the cell state has taken effect. Add the storage buffer to a bind group because it's part of the group as a uniform buffer. Add the same bind group in JavaScript code as well. Add the storage buffer like this. Aha, here's our bind group that we made before. Let me find this in JavaScript. TypeScript, whatever. Bind group. Shice. I think I gotta put this at the very end, right? I really need to sit down. Like, what the hell am I doing? I should not be doing this while standing. Like, I should not. I have to find a spot to sit. Because I can't work like this. It's crazy. Crazy. could find a spot. I don't know. What do I want to do? Okay, hold on. Crap. Freaking A. You know what? No. I shouldn't be going this way. I should not be going this way. I gotta be going back. Where the frick is like a seat? Fine. I might as well. There's this cool spot. It's kind of out of the way. But I'll be able to sit and I'll have like a good ass view. Oh. Okay. Okay, sorry for this intermission, but like, it can't work right now. Like I thought I could, and I got a little bit far, but I noticed that I was only doing my good progress when I was actually, sitting down like a normal human being. Human being. Might as well. Whoa. Damn. Crap. What do I want to do? Shite. Is this a mall? I don't think I can go inside there while I'm live streaming. That would not work. Because why can't I? Because there's security. Oh, they want me to put my laptop in a bag, which I am wearing a bag, but that would require me to pause the live stream. And that's not going to happen. I need to code this. Crap. Need like a better view, maybe. Okay, yeah. I know where I'm going. There's a cool little walkway spot. The best part is I can walk back easily. Okay. Is there shade here? There's shade here. There's no table I can sit on. What do I לעשות. Sorry if you're tuning in and you're just like not knowing what the hell I'm doing. It's just I need to find I'm looking for a spot where I can sit. Let me explain myself more I need to explain myself more like rigorously. I need to find a spot that allows me to sit. Jesus. When I find a spot that allows you to sit, I will be able to code more effectively. That's the goal. So, okay. Oh, crap. Alright. Where do I want to go? Scheiße. It was, where was it? IMAX. No, Max. Sorry, I just read a sign that looked like IMAX. Okay, it's this way, Okay. What I need. Over here, I'm pretty sure. Oh, whoa. There's a market there. This, I think this is the way to go. I think. Ooh, there's a Ford shop. How's this view? There we go. What the hell is here? Wait, this is not the place to be. Where the hell do I go? It's a construction site. No, I think I took a wrong turn. Maybe. Yeah, no, this is the wrong way. Crap. Just need some shade, man. I need some freaking shade. Okay. Bind group. What am I trying? I'm trying to get a compute shader. If I get a compute shader to work, then it will be good. Oh my God. Okay. George and Lydia, Weiss building, Gate of Life. Very nice. This is the way, yeah? I think this is the way. Okay. I don't think I'm gonna find my spot yet. Big yet. But this is gonna work as a temporary one because there's shade. And that's the important part. I need shade. Oh my god. Shade. Here we go. Okay. I gotta pause. Alright. Good. Found a spot. Frickin' hell, man. Okay. Bind group. I need to put this bind group in another spot. Where exactly? The bind group needs to go right over. The bind group has to go elsewhere. So this is my original bind group. Buffer has to be. Oh, a new entry. Aha. So entries, aha. Binding, that binding is corresponding to 1. But aha. I want a new binding. This is going to be binding 1. Like so. And now I want to make a new binding. Which the binding is going to be equal to 1 this time. And the resource is going to be equal to a buffer of a... Now I got to move this whole thing down. Just a moment, because I defined it below here. This goes right before the pass, I think, right? Yeah, I'll do it right before the pass. Okay. Nice. Bind buffer has to be equal to the compute buffer. What did I call it? Damn it. I called it cell pipeline. Where's my for loop? I wrote a for loop somewhere here, right? Yes. It's called the cell state storage, right? Cell state array? No, what's the buffer? Yeah, cell state storage. Cell state storage. It's a buffer, okay? Comma there, good. Make sure the binding matches the entry, the binding corresponding. With that in place, refresh, and we get... Not quite. No. Another buffer. Wow. Alright. In that case... Whoops. What went wrong here? What's going on? Why is it just half the size of the buffer, of the grid? Like, why is it doing that? That is very strange. That is very, very strange. Why is it doing that? Every third. But why are they overlapping like that? Did I modify something? Bruh. This is not going as planned. This is not. me try this again. Color grids. All right. I'm gonna make this a copy and just call this like backup. Copy, paste, backup. I'm gonna put my color grid in here again. Refresh. What the hell? Color grid. What's the issue here? What now? Now my backup stopped working? That's literally not the point of a backup. Backup needs to work. Oh, shit. Get rid of all this stuff. Does this work? What the hell? Oh wait, this must, no, this has gotta be, it's gotta be maybe my shader. Yeah, it's a shader error, sorry. It is a shader error. Bro, how do I do this? If there's a shader. Damn it. All right. Big ass speaker appended to the truck. Okay, what do I want now? Frickin' hell. Why is the grid only half size now? Something changed and I lost my backup because I'm editing multiple files. This is prone to happen, ain't it? Ain't it prone to happen? I'm back here again. Frick. Where am I going? I thought I knew the way. Guess not. How did I get there? I'm looking for a place. Damn it. Might seem like this construction. I don't know. It seems like I'm starting to see, like, I'm just realizing this live stream might not be a good idea because, oh, now I'm realizing that. No, it might not be a good idea just because, like, I'm not really interacting with the audience, and it's like, why do they want to just see me walk around? So this is definitely like autobiographical. This is probably just like for me, yeah. For whatever value it's worth. I do this, man? Why you half spots? What happened? It's because I'm multiplying. Let me go back to the vector thing. Where do I multiply it by the state? Get rid of that. Oh. That's why. 2 times. Oy, oy, oy. Okay. Is that it? Yeah. Okay. I don't see that pattern. I see a different pattern appear, but whatever. Whatever. It's perfect. So, what next? If I want to get that pattern, I want to get something different, which is ping pong buffer. Most simulations, like the one you're building, typically use at least 2 copies of their state. On each step of the simulation, they read from one copy of the state and write to the other. Then on the next step, flip it and read from the state they wrote to previously. This is commonly referred to as a ping pong pattern because the most up-to-date version of the state bounces back and forth between state copies each step. 2 copies. From one copy and right to the other. Ping pong, ping, boing, 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 boing. Because we have the previous state and the next state. They flip it and read from the state they wrote to previously. This is commonly referred to as ping pong. Why is that necessary? Look at the simplified example. Imagine you're writing a very simple simulation in which you move any active blocks right by one cell each step. To make things easy to understand, you define your data and simulation in JavaScript. Example simulation, don't copy into the project. State 0, let state iterate through the state list. If it's equal to 1, make it 0, and the next one becomes 1. Simulate, run the simulation for one step. But if you run that code, the active cell moves all the way to the end in one step. Why? Because you keep updating the state in place and move the right active, and then you look at the next cell, and hey, it's active. If we move right again, the fact you change the data at the same time corrupts the result. Blah, blah, blah. Yes, you don't want to plow through the whole thing at once. Like, if you keep using the same state and you keep on overwriting it, then yeah, you're gonna lose what the original was to begin with. You don't want that. That's not good. That is not good. So what do you want to do instead? You want to, what is it? Instead of that, you want to do something different. Example simulation, don't copy into the project. State A, state B. Simulation, oh, this is also don't copy the project. What you want to do is you want to make the function simulation take in the input and the output. We're reading it separately. So you just made a function with parameters. Yep, gotcha. Simulate state. Use this pattern in your own code to use this pattern in your own code by updating your storage buffer allocation or to create 2 identical buffers. What do I want to do? Create const cell storage device, create cell state A, cell state byte length. To help visualize the difference between the 2 buffers, fill them with different data. Alright, create 2 storage buffers. I want to create the cell state storage. This is going to have 2 buffers. First buffer is going to be cell state A. Second one's going to be cell state B. I'm going to put that in the cell state buffer. Where is it? Where is my cell state buffer? TS, game of life, cell state, cell state. Cell state buffer. Cell state array storage. Where did I device.create? Where did I put that? I think I put that over here, right? Cell state storage redeclared block. Aha. Got it. Yeah, before, all right, yeah, it's a different type now. But the gist of it is, and, where is it? Cool. Get rid of this old one. Now this is the wrong type. Thank you, TypeScript. So we have 2 buffers. This is a list of 2 buffers, okay? Okay. There are 2 buffers inside of here. One of them is a cell state A. It's literally just immutable. It's the size of this. It's meant for storage, and it's meant for storage. So we're going to be writing to both of these. To help visualize the difference between the 2 buffers. Oh my gosh, that's really smart. I would have just copied it over or swapped the pointers. But they're not even swapping the pointers. They're actually just running it backwards. To help visualize the difference between the 2 buffers. Oh, wow. Did not expect that. To help visualize the difference between the 2 buffers, fill them with different data. Mark every 3rd cell of the first grid as active. For I is equal to 0, cell length of array, blah, 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 blah. You take this guy and you put it right over where? Right buffer, you don't have to preserve the contents of typed array anymore. Frick. Alright. So I'm going to tab this, tab, undo the tab of the first. So I want to get EastLint. Frick. No, I don't want to set up EastLint. It allows me to do quick fix. I won't do that. ESLint, it's like you can be strict with it, and if you get the wrong like tab sizes, it can just automatically change it. Well, it can warn you that you should change it, and then you need to activate the change. So you're going to get a lot of errors. Non-crucial errors. Right buffer, you don't preserve the contents and stores typed array anymore. At that point, the content can copy the GPU buffer. Blah, blah, blah. To show different storage buffers in your rendering, update your bind groups to have 2 different variants as well. Bind groups. 2 different. So now I'm going to go to bind groups. So what did this do? Oh, yeah. So this is a bad line. I don't want to do that anymore. Oh, because I'm already doing it here. Mark every 3rd cell of the grid as active. Blah, 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 blah. Cell state array. Oh, is this just the initialization? So where did my old for loop go? Oh, I think, yeah, I just got rid of it. Yeah. Cell state. Bind cell state array, blah, blah, blah. So this, for every 3rd cell, set it to 1. Then you write this buffer as 0. Binding 0. Why binding 0? Oh, no, offset 0. This is offset by 0 bytes, which is what we want here. Secondly, move for the taxi, which is exiting. Okay. What we want is, yes, I'm in front of a part of a parking garage. What I want is to get cell state 0, %2, right buffer. Mark every other cell the second grid is active. So what's the difference here? This is every other cell. This is every 3rd cell. Why is the formula different? I don't know. Sure, whatever. Mark every 3rd cell of the grid is active. Every 3rd cell of the grid is active. Makes that. All right, now it's my bind group. Create bind group. Okay, let's see what's going on here. My bind group Oh. Yeah, another car. This is a bad place to work. Okay. What I want is another bind group. So let me make the bind group here. Const bind group. What's the difference between these? So I'm no longer get group layout 0. What does that even return? GPU bind group layout. Sure, okay. Let's just get rid of the old one. It's not what we need here. It's confusing me only. Oh wow. There's a lot of action going on here. Where's my error? I have an error somewhere. Where? Where is the error? Aha. It said bind group. Bind groups. Aha. Shice. Cell renderer bind group A. It takes uniform buffer and the cell state storage of 0, which is the first one. And then group bind buffer is the exact same thing. There's 2 bind groups, but one of them's for A, one of them's for B. But they have the same uniform buffer. They're both calling on the same data, I think. So what do I want to do? Bind group, set up a render loop. Oh, damn. Okay, well, I still have an error now. What? Let me fix the error. Set bind groups, but this is the wrong type. Set bind, okay, I'll leave that there. We have to fix that. Oh, this is where it's gonna be. Oh, when we request the frames. So far, you've only 1 draw per page refreshed, but now you want to show data updating over time. You need a simple render loop. A render loop is an endlessly repeating loop that draws your content to the canvas at a certain interval. Many games and other contents that want to animate smoothly use the request animation frame to schedule callbacks at the same rate the screen refreshes, 60 times every second. This app can use that as well, but in this case, you probably want updates to happen in longer steps so you can easily follow what the simulation's doing. Manage the loop yourself instead to control the rate. First, pick a frame rate. Okay, this is going to the top of the file. This is my configuration stuff. Then move all the code you currently use for the rendering to a new function. All the code for the render. Oh my gosh. Then move all the code you currently use for rendering into a new function. That's the encoder and the pass. So, okay, I agree. That makes sense. Let me put this at the top here. Actually, no. This has to be inside. So everything when I make pass, encoder, begin, render, pass. Where's the encoder? Let me put my render pass right over here. Tov. Okay. What if I, so instead of that, I want to get instead a bind group or, no. Oh. Updated. That one's updated. So let me do it. Oh, this is a okay, it's a function. So, okay, got you. So is this inside the function? The encoder is inside the function. All right, let me make this a function. Update grids. Hold on. Update grids becomes this. Where does this end? It ends after the device queue. Wow. Cool. Alright, that's where all this function exists. All of this exists inside the update grid. And now I'm going to schedule it to update repeatedly. Schedule update grid. This is classic JavaScript-esque. I don't know what the hell it's doing. We'll set interval. Technically, oh, we're just setting interval. But we're not doing request animation frame because that's 60. Yeah, okay. Manage the cell state. All right, so I think that's it. Oh, but we need to adjust this line. So instead of that, we want to do bind groups, but like such. Refresh. No, 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 no. Yep. Oh, yay. It's not working. Let me run this a little bit slower. Let me do it every 5,000 because I don't want to spam it. What's going on here? Destroy texture while calling Q submit. Where's the submit supposed to go? Draw the grid, update, blah, blah, blah. Color code, pass. Whoa, that's way different. No, it's the same. Frick. I don't want to actually like call this a function. No, no, no. This should just be. This should all just be inside of it, you know? Like, I don't want this to be a function. Cool. This is the second argument of our set interval. No, the first argument at update interval. This occurs at update interval, blah, 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 and it's the second argument. Set interval, good. Does that work? Nope, doesn't. Oh, did it work? Oh wait, it did work. Oh. I jumped the gun. It's not changing. Alright, let me undo that then. It was working. Let me just increase the, the speed. No, now it didn't work. Alright, so. Crap. So this does work. Let me just set the interval speed to 500. 500, refresh, bam. Only refreshes once, so why is that? I don't know why it just refreshes once. That is so strange. Frick. I don't know. How do I do this? Okay. I gotta change my... Oh, I gotta drink some water first. Okay. Okay. What do I want? What do I want? Okay. Oh boy. Okay. What do I need? Let's go. I need to just cool down. Cool down, cool down, cool down. Wow. Urgh. Frick. So it didn't do the thing right. Hold on, so it should why doesn't it stop? Sorry, why doesn't it change? The interval, according to the Google guide, when it initiates the second frame, it should read the second buffer. But it's not doing that. So I don't know what's going on. Okay. What do I need? What do I need? There was a view that I had before. I had a view. Aha, is this it? Maybe this is how I get there? There's a place that I was working at previously. But how did I get there? There it is, I think, right? I think it's this way. I don't mind visiting it, I was there before. Just those sirens are me. Never mind them. I'm trying to look for a pathway alongside a cliff, because I worked there recently and I really like that spot. Just don't know how I got there. Some way. I don't know how. What do I want to do, man? Magen David Edom. Is this it? Where? Blue Rose Development. Where do I go? I think this is the right way. David Adom בישראל. Where is it? Here? Is this it? Hold on. around it. So I don't know where I walked last time. Okay, I might as well show you. So I'm gonna do a 180. I don't think there's gonna be like people looking weird. This is like a little pathway. And then when you exit the pathway, what is it? Bam. There is not much shade here, I think. So I did go here. What the heck, man? Come on, man. All right. Oh crap. Okay. Scheiße. Okay. What do I want to do? Desmos. Oh! Super Llama. Howdy. Thank you for tuning in. WebGPU is so confusing, even more than WebGL. Oh, thank you. I'm very, very glad. You are the first person to pop into the live stream. There's another person who popped in prior, but, comma, he was here for Minecraft, not for the coding. So I'm very, first of all, off the bat, I'm very, very happy that you've identified what I'm doing. So, is it more confusing than WebGL? That is a good question. I have not used WebGL before, but the thing was, I read like some criticisms of it, at least in this Google article. I'm looking at a Google article to teach me how to do it, and they're saying some limitations of WebGL, which are unfortunate. It's unfortunate that they exist. So I haven't learned WebGL formally, but if there are those limitations, then I want to get rid of those as soon as possible and jump right into the hard stuff. Because I kind of enjoyed writing code in like C, which is like, I think C is like, I'm never going to use C, but it's good to know. I want to know how to use a GPU, render fast graphics, and like really be in control of it, like really know what I'm doing, kind of. That's the mission. We'll see if it pans out, but I don't know if it will. That's what I want to try. So where's what do I want to do now? Okay. What do I want? I want to do a thing. Web GPU, first web app, draw the grid. So this is all inside of our... Aha, I forgot this, didn't I? That's why. I forgot one important line. I forgot to increment this. My bad. Now it'll work. It's gonna go back and forth now, right? There we go. Oh my gosh. It's actually moving. Whoa. I need to find a better vantage point, because you're not here just to watch a blue sky. You're here to see the scenery and the coding. You're here for both of it. Wow. Holy cow. So, as you can see, in addition to this view currently on display, we have what is it? We have the canvas animating. We're updating the frame step routinely every 500 milliseconds. That's why it's happening 2 times per second. So that's good, actually. I'm very happy. I was like, why isn't it updating? And then I was like, I gotta take a walk now because it's not updating. And when something's not working, you gotta step away. You gotta walk away for a little bit. Fresh pair of eyes. Here we go. Is this good? Oh, is this good? Don't fall, don't fall. Nice. How is this as a working location? That's crap. Because of that little box thing there. Nah, you don't want any of that. You just want to get pure view. Holy shit. This is insane. Like, why am I coding here? Sorry, I gotta show you the code, otherwise you're gonna forget this is a coding video. Here's the code. Yeah. So, not only do I have to find a spot where I can work, I need to find a spot that I can work that has shade. That is an important step. Because if there's not shade, I'm worried that my computer is going to explode. Ugh. Ugh. All right. What do I want to do? Oh, perfect. I think this works, right? Yes, okay. Oh, there are people coming. Nope, they're turning a corner. Whatever. I don't care. I do not care. If I cared, I wouldn't be doing this. Okay. Whatever. That's as good as it's gonna get. Game of life setup interval. All right. So I actually do want to make this. I actually do want to make this a function. So that requires taking everything inside of here, copying it, and I'm going to name this function. Whoops. No messages. I'm going to name this function update grid. Function update grid. No parameters. Oh, I think it's just this, right? Yeah. Function update grid is equal to this. There. Local function updates blah 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 blah. Local. Okay, cool. And now we call the function update grid. Cool. Refresh. Should still work. Nice. Butte. Okay. Now, encode a render pass. Blah, 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 blah. Schedule. Back and forth between two. And you're pretty much done the rendering side of things. You're all set to display the output of the Game of Life simulation to build in the next step where you finally start using compute shaders. There's so much more to WebGPU's rendering capabilities than the tiny slice that you've explored here. The rest is beyond the scope of this code lab. Hopefully it gives you enough of a taste how WebGPU's rendering works, though, that it makes help exploring more advanced techniques like 3D rendering easier to grasp. Oh yeah. Run the simulation. Now for the last major piece of the puzzle. Performing the Game of Life simulation in a compute shader. Use compute shaders at last. You've learned abstractly about compute shaders throughout this code lab. What exactly are they? Compute shader is similar to vertex and fragment shaders in that they are designed to run with extreme parallelism on the GPU. But unlike the other two shaders, check if anyone's there. Oh, why am I outside? It's a good question, Super Llama. I'm feeling spontaneous. And also, my room, pausing the coding. I'm outside because my room is a Faraday cage, which basically means that I'm currently living in like a little apartment room, but when I'm inside the apartment room, my upload speed, it's like non-existent. It's just totally gone. 0.2 megabits to be precise, or lower. So as a result, I've grown comfortable with working outside. for the past month, I've actually just like, for my actual job, I find a bench outside, and I've been getting bored of that same bench. So now I'm just finding spots to work and showing around where I'm at. It's kind of for me. Why am I outside? The truth is kind of for me, because I want to see this later and be like, damn, I was there. And that would be like, whoa, I coded there? What was I doing? It's very strange. Is it conducive to me coding? Certainly not. No way. But it's fun. And I apologize if this is at your expense. If you are bothered by like the setting, feel free to click off. Because it is like, this is not presentable. I will say right now, for a stream, this is like, you have to go out of your way to actually like enjoy the content here. Anyways, use compute shaders. So blah blah blah. A compute shader is similar to a vertex and fragment shaders, designed to run with extreme parallelism on the GPU. But unlike the other two shader stages, they don't have a specific set of inputs and outputs. You are reading and writing data exclusively from sources you choose, like storage buffers. This means that instead of executing once for each vertex, instance, or pixel, you have to tell how many invocations of the shader function you want, and then when you run the shader, you are told which invocation is being processed, and you can decide what data you are going to access, which operations you are going to perform from there. Compute shaders must be created in a shader module, just like vertex and fragment shaders, so add that to your code to get started. As you might guess, given the structure of the other shaders that you've implemented, the main function for your compute shader needs to be marked with the compute attribute. Compute is a compute shader. We are going to be crunching numbers with this. Create a compute shader with the following code. Let's see. Oh, got a little fly over there. Create a compute shader with the following code. Compute shader module. This is called the Game of Life Simulation Shader. Aha! This is going to... I'm going to put this before the updates, right? Right buffer, bind groups. I'll put this before the bind groups, sure. I'm now going... Alright. So now I'm actually going to call this. I'm going to call this something new. What's my error here? I'm getting an error still. Context is defined. No, it's defined. I mean, well, I'll just, I'll be safe. Actually, no. I'll just make it, I'll just tell it to shut up. Because it's inside a function within a function, it doesn't know if context is defined, yada, yada, yada. Update grid, color grid. All right, when am I going to be backup of this? Switchy. This is going to be the switchy one. Switchy means it just switches back and forth. But now I'm going to import a new file. There's the grid shader, and I'm going to import the compute shader from a compute. It's not called a compute shader. It's called a... Yeah, it's a compute shader, whatever. Shaders, I'm going to call this compute.wgsl, and now I'm going to make that the file. This is going to be called compute.wgsl. What is the contents of this? Like this. Oh, the code is, whoops, fn compute main, like such. Nice. Because GPUs are used frequently for 3D graphics, compute shaders are structured such that you can request that the shader be invoked a specific number of times along XYZ. Oh, wait. Sorry, I forgot. I still got to put it inside of here. compute shader. Whoops. And the code is literally the compute shader. It's a string. Okay. Hey, why aren't you working? Oh, sorry. Don't need that there. Cool. This is still going to work, right? Tint reader failure. Aha. So I got an error for the compute shader. That's because there's pretty much nothing inside there. GPUs are used frequently for 3D graphics. Compute shaders are structured that you can request the shader invoke a specific number of times along an XYZ axis. Lets you very easily dispatch work that conforms to a 2D or 3D grid, which is great for your case. You want to call the shader grid side times, once for each cell of your simulation. Due to the nature of GPU hardware architecture, this grid is divided into work groups. A group has an XYZ size, although the sizes can be 1. There are often performance benefits to... whoops, hold on. Where is it? There are often performance benefits to making your work groups a bit bigger. For your shader, choose a somewhat arbitrary work group size of 8 times 8. This is useful to keep track of in your JavaScript code. Define a constant for your work group size, like this. I think I need to turn on battery saver. I'm on 20%. There we go. Yeah. I'm just reading in the air. Define a constant. For your work group size like this. Work group size is equal to 8. You also need to add the work group size to the shader function itself, which you do using JavaScript's template literals, so you can easily use a constant you just defined. Add the work group size to the shader function like this. Alright, yeah, work group size. What's... For your shader, choose a somewhat arbitrary work group size of 8 times 8. This is useful to keep track in your JavaScript code. Okay, put this at the top of the file. I'll put this, blah, 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 blah. Work group size is equal to 8. Tov. You need to add the work group size to the shader function itself, which you do using JavaScript's template literals, so you can easily use the constant you just defined. Add the work group size to the shader function like this. Compute, blah, 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 blah. Oh, whoa. New line. To your shader function. Work group size is equal to work group size by work group size. I don't know why it's 8 by 8. This tells the shader that work done with this function is done in 8 by 8 by 1 groups. Any actually leave off defaults for 1, I'll leave specify the x-axis. Note, for more advanced uses of compute shaders, the work group size becomes more important. Shader invocations in a single work group are allowed to share faster memory and use certain types of synchronization primitives. You don't need any of that though, since your shader executions are fully independent. You could make the work group sizes 1 by 1 by 1, and it would still work correctly, but that also restricts how well the GPU can run the shader in parallel. Picking something bigger helps the GPU divide the work better. There's a theoretical ideal work group size for every GPU, but it's dependent on architectural details that GPU don't expose, so usually you want to pick a number driven by the requirements of the shader. Lacking that, given the wide range of hardware the GPU concept may run on, 64 is a good number that's unlikely to exceed any hardware limits, but still handles large enough batches to be reasonably effective. Okay, we'll see what a work group is. I'm going to have to come back to what that actually means later. So as with other stages, there's a variety of built-in values that you can accept as input to your compute shader function in order to tell you which invocation you're on and decide what work you need to do. Add a built-in value like this. Compute, work group size, what's the argument of our compute main function? Compute main function becomes this. So this goes inside the parentheses. Compute main, a built-in global invocation ID, that's what it's called. Eh. You passed in the global invocation ID built-in, which is a three-dimensional vector of unsigned integer. A three-dimensional vector of unsigned ints that tells you where in the grid of the shader invocations you are. Sure. You run the shader once for each cell in your grid, you get numbers like 001, 10, all the way to 31, which means you can treat it like the cell index you're going to operate on. Okay. Sure. We'll see. It's a bit strange. Uniform shaders can also use uniforms, which you use like the vertex and fragment shaders. Use a uniform to compute shaders, tell you the grid size like this, blah, 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 blah. Built-in group, oh, I'm creating a uniform. So again, a uniform is something that you grab from outside. I'm going to call it a grid. Just like in the vertex shader, you also expose the cell state as a storage buffer. In this case, you need two of them because compute shaders don't have a required output like a vertex position or fragment color. Writing values to a storage buffer or texture is the only way to get results out of a compute shader. Use the ping pong method that you learned earlier. You have one storage buffer that feeds into the current state and one that writes out the current state. Expose the cell input and output state to storage buffers like this. Oh my gosh. Oy vey. That's like, bruh. Man, I don't know. I'm just like, I don't know if I have the bandwidth to continue. How long have I been streaming? Shice, 2.5 hours. Just like one continuous shot. That's pretty good. I'm gonna continue. Wait, when's my meeting? I have a meeting today with some coworkers. I meet with them in an hour and a half. Shite. Oh my gosh. I think I gotta like wrap it up. Just when I got to compute shaders, I gotta wrap it up. Freaking hell. I mean, like, I think this was a success. I walked around a lot. I mean, I didn't really talk to anybody. Aside from, thank you, Super Llama, for attending. That's it. Because I did a live stream like this 2 years ago. And it was, like, one of my favorite live streams. Like, it was actually, like, I would describe it as, was it? No, it was 1 year. Oh, it was 2 years ago. Yeah, it was 2 years ago. It was such a fun live stream. But that was the right hour. That was the right hour. Because here it's like people are just waking up because of my time zone. What time is it now in like EST? It's like my go-to. Yeah, it's like 8:30 in the morning. Like who the hell is going to watch YouTube? I mean, maybe I can like continue for like a little bit. Ugh. Okay, I do need to eat something. So, how about this? I'm going to take you, continuing on the walk. Shice, this is freaking hot. I want to continue on the walk, and we're going to make it to the, like the food area. All the nice foods. And then I think I can log off. That'll be like a good time. I'm shocked that this time my Mac has drained quicker than my phone. Yeah, my phone's at 58%, which is interesting. So it's lasted. My power is at 20% right now. Let me actually look at I can actually look at the chart. Battery history, usage history. Yeah, that's steep. That's really, really steep. Just as reference, yeah. Like this was me yesterday. It kind of dropped off like that. That was gradual. I would say that's like 5 hours, but this is just like, yeah, the starting 13. That dipped. That really dipped. Yeah. Gotcha. It's good to know. All right, let's save checkpoint. All right. Got up to the compute part and push this. Excellent. Oh, is it Git public? I think it's public. Not like anyone cares. You could get this all yourself for Google. I'm gonna continue down this one day. But for now, yeah. Let me start heading back. Oh yeah. Ain't gonna litter. That's not cool. Thank you, tree. Why'd I even say that? Ain't gonna litter. That should be redundant, right? Well, here. Yerushalayim in Jerusalem. Lots of garbage. Lots and lots of garbage. Okay, let's continue. Shit. I think I'll just get like an overview, like reading it instead of. Note that the first. Shut the tab. Note that the first storage buffer is declared with var storage, which makes it read only. But the second storage buffer is declared with var storage, read and write. This allows you to both read and write. This allows you to read and write to the buffer, using that buffer as the output for your compute shader, and there is no write-only storage mode in web GPU. Next, you have to find a way to map your cell index into the linear storage array. This is basically the opposite of what you did in the vertex shader. Shite, I think I'm dehydrated. I should not continue talking, actually. This is a terrible idea, bro. Yeah, I'm not getting anything. Yeah, you know what? Let me close the stream. I'll just give like a final view of what the outside looks like. I gotta shut this off. This is like, it's taking a toll on me. But it was a good shtick, I think. Yeah, to anyone who's like clicking on this afterwards, thank you for watching this